Iman. Okay. Okay, last good. I think 6 of you, yeah. Okay, so let's restart for today's lesson. Okay, just as usual, some small recap what we learned about oscillation. Okay, everyone can hear me? Can see the document?
Yes, yes.
Can see the document. Okay, good, thanks. Okay, so oscillation. So I introduced with you. I told you what is meant by simple harmonic motion. Okay, it takes a placement. Then recently, okay, guys, sorry, can you hear me?
Yes.
Is it disconnected just now?
Just 1 second.
Just 1 second, Okay, thanks. Okay, so we learn about the velocity and acceleration in terms of displacement, and graphical illustration for changes of displacement, velocity, and acceleration. Okay, here you need to draw the graphs. Okay, so for x, v, and a in terms of time, I think you know that how to draw. Okay, so taking x naught sine omega t, omega x naught cos omega t. This is negative omega squared x naught sine omega t. So you know how the graph looks like. Then Vx, Ax graph, you should know. Vx is what? It's a circle. Okay. What? Omega square root of x naught square, x squared. And Ax is what? Negative omega squared x. So the graph looks like what? A versus x. Straight line with a negative gradient. Okay. Then now we talk about energy that day, yesterday. So energy is found to be, these are the two formulas for energy. Okay. There is a mistake here. On top should be EK. This should be EK. This is your EK, kinetic energy. Kinetic energy half m omega squared x naught squared minus x squared. Potential energy is half m omega squared x squared. How the graph looks like? So this is the total energy formula. Okay. So how the graph looks like for EK? Anyone? EK versus x, smiling face or sad face? Kinetic energy. So it's a sad face. Sad face, and EP should be your smiling face. Should be the other way around. Okay, smiling face. It's your EK. This is your EK. It's your EP. Okay. Okay, so yeah. We go back to the PowerPoint. Okay, so summary. Kinetic energy is a sad face. Potential energy is a smiling face. The kinetic energy, if for the first version, the kinetic energy in terms of time will be a cos squared graph. For potential, it will be a, what graph is this? Anyone? What graph is this? If kinetic energy is a cos squared graph, means potential energy in terms of time will be what graph? Anybody can predict?
Sine squared.
Sine squared graph. It would be a sine squared graph. Opposite lah. Kinetic drop by 1 joule, potential should rise by 1 joule. If kinetic is cos squared graph, potential going to be sine squared graph. Okay. Yeah. This is for the first version. The time starts 0 at the center. If time start at the edge, then how kinetic graph going to look like? What graph? If time start at the edge, kinetic will be sine squared graph. Potential will be cos squared graph. The other way around. If the time start at the edge. Okay. So, but whatever it is, one of them will be sine squared, another one will be cos squared for energy. Smiling set phase go for energy in terms of displacement. Okay, so yeah, so E total we know is EK plus EP. So the total energy is half m omega squared x naught squared. So this is how the graph looks like. Energy versus time. EK is looks like cos squared graph, and EP is like sine squared graph. This is the time start at the center. The time 0, EK found to be maximum. And down is the energy in terms of displacement. You have 3 graphs. Set phase for the EK, smiling phase for the EP. Straight line is what? Straight line is the total energy. Total energy just a straight line, because energy always constant. Okay, the total energy is half m omega squared x naught squared. This formula not only for total energy. Okay, this formula is also for EK max. EK max also half m omega squared x naught squared. And this formula also for EP max. EP max also half m omega squared x naught squared. So EP max, EK max, E total, same formula. Okay. So you know last time you learned wave. You learned wave. Wave, intensity proportional to the amplitude square, right? So AS knowledge. But intensity is what? Power over area. Okay, intensity is power over area. Power is what? Energy over time, area. The energy of a wave is actually in form of wave produced by an oscillation. Oscillation. So the energy of a wave is following this formula. So energy of a wave is found to be directly proportional to the amplitude square. That's why intensity is said to be proportional to amplitude square for wave. Because oscillation produces wave. This is the proof for intensity proportional to amplitude square. What is the proof? This is the proof. E total is half m omega squared x naught squared. E total proportional to amplitude squared. Okay. Any questions, guys, from here? Oh, okay. Okay. So, one question. Come on, give a try. Try to figure out how do you go about. 1 minute for you. Give me the answer for this. Of course, the next slide is the answer. But try to figure out before we check the next slide. Okay, you got the answer for the first one? What's the total energy? Particle of 60 gram, frequency is 6.3, amplitude is this. So straight away, total energy is what? Just half m omega squared x naught squared. Don't get confused when to put x naught, when to put x. For the maximum value, all it will be x naught, fixed value. So M is 60 gram, change to kilogram, omega 6.3, and X naught is 15 mm, change to meter. And you get the answer in Joule. So hope you get the first answer. 2.7 times 10 power negative 4. Make sure all are SI unit. Okay. Okay. I think A is straightforward. Try to do the B. Find the kinetic energy and potential energy at half amplitude. That means at the displacement of 7.5 lah. So what is your EK formula? Kinetic energy is half m omega squared x naught squared x squared. Let's come to your mind. So half m, of course, again the mass. Omega, the omega given on top. X naught is what? X naught is 15. So 0.015 squared minus x is the new displacement line, 0.0075 squared. Okay, so you get the energy. Okay, important is what formula to be used. Half m omega squared x naught squared x squared. EP is what? Half m omega squared x squared. So the x you put straight away, 7.5 change to meter. So yeah, so this should be the working, right? So half m omega squared, the x naught x, put it correctly, change to meter, and you get that. So remember, at the half displacement, half of the amplitude, the energy not same, they're not equal. At the half amplitude, potential looks like greater than the kinetic. Okay, so don't think when a pendulum, if the displacement, maximum displacement is 10 centimeter x naught, when the displacement is exactly 5 cm, don't think that EK and EP same value, like half, no. EP looks like greater. Okay, all you get to know about when you sub in into the formula. Okay. So any questions, guys? Can you hear me, everyone?
Yes.
Yes. Can. Because I'm always afraid lah, because suddenly disconnected the previous class. So other classes, so I need to check every time.
Oh.
Okay, this is practice the same way. Find the kinetic energy, potential energy, total energy. Use the formula, you can get the answer. Okay, we skip this. Okay. Okay, so you can check the working. Okay, it's the same style. Okay, so now we already reached the last part of this topic. Okay, the first half is full of calculation, investigating about the speed, velocity, acceleration, kinetic energy, potential energy, total energy. Now our discussion is about all qualitative, what do you call theory, explanations. Okay, so oscillation got many types. As of course is SHM. You have free oscillation, you have forced oscillation. Okay, if you hang a spring and you let it pull it down and let it go, it oscillates. It's called free oscillation. Okay, free oscillation means it oscillates without any external force. Okay, a free oscillation, body oscillate at its natural frequency and is unaffected by external force. No other external force is given. Not the gravity, not gravity all included lah, but not like there is a machine to push it down. Okay, so free oscillation in exam they'll ask if you heard about natural frequency, right?
Yes.
All of you heard about natural frequency, yeah? Okay. Do everybody like a back, like your part of your body, like your kidney, your liver, your heart, all of them have their own natural frequency. Do they have same natural frequency or different? They have a different natural frequency. Different organs have a different natural frequency. Different material will have a different natural frequency. Okay, so when something oscillates naturally, the frequency oscillating is called natural frequency. Okay, so the total energy of the free oscillating system remains constant. Anything move freely, we assume the energy is constant. So EK plus EP is the E total. But not always is going to be a free oscillation. Free oscillation, the no loss in energy, amplitude remain constant. In exam, they will ask the second one. This is called damped oscillation. What is meant by damped oscillation? The energy drops. A system where the energy is lost. What is the indication that it's a damped oscillation? The amplitude decreases. Okay. In exam, if they ask, what happened to this oscillation? You say damped oscillation. What is the reason? You said energy loss, and don't forget to say amplitude decreases. That's the indication. But when you do damped oscillation, yeah, the amplitude will drop. Okay, so damping. What is meant by damping? Damping, the amplitude of the oscillation or oscillating system will decrease exponentially. Okay, damping is the process whereby an oscillating system lost energy, resulting in a decrease of amplitude. The amplitude decreases. Okay, may occur because of course, some resisting force like air resistance, in the air, viscous drag, maybe in the liquid, frictional force if it's on the surface of the table, maybe radiation in terms of sound. This all going to lose energy, causes it to damp. So what is damping means? It's a type of oscillation where the system, oscillating system, loses energy, results to decrease in amplitude. Okay. Okay, now comes to the another one important part. Scientists found that damping got three type of damping. Underdamped, critical damped, heavily damped. The one in your lab, when you do the pendulum experiment, is your light damping, the first one. Okay, light damping very frequently asked in exam 2 compared to other two. Light damping, the amplitude is going to reduce gradually without changing the period. Period won't change. Okay, see the earlier one. The earlier one here. This is the light damping. Why I say the light damping? The period never change. Free oscillation and the damping oscillation, the period still the same. So light damping period won't change. Only the amplitude drops. Okay. So that's light damping. The system oscillates with decreasing amplitude over a period of time. Okay. So that's a lab. We have another type of damping called critical damping. Critical damping, the graph is like this. What is critical damping? Critical damping. You see, this is your displacement. You have a spring. Let's say you have a spring. You have spring. The spring has been compressed. You compress the spring. Okay, the compress the spring originally was a certain height. Okay, you compress the spring. So this is the displacement x. The displacement. So the displacement is this x. When you let it go, if it's a critically damped, what happened? The displacement straight come to what? Come to 0. Means what? The spring will straight, when you compress, let it go, the spring straight away come to this position, come to the equilibrium. Normally the spring will oscillate about equilibrium. But if it's critically damped, the system will come to equilibrium, loses energy, then stop moving. This is called critical damping. Okay. So what time we're going to reach the time? Normally it's a quarter period. Quarter period. That means quarter period means immediately come to 0, come to equilibrium. Okay. The system does not oscillate. Yeah, it does not oscillate. It just come to, its mission is come to equilibrium. You extend it. If it's critically damped, let it go. It go come to equilibrium. That's it. You never go up. The system does not oscillate, but returns to its equilibrium position in the shortest time. This is called critically damped. You need technology to do that. Okay, critically damped. Heavy damp, light damping, just wind blow can do that. But critically damped, you need to have the specific force, resistive force to stop it at equilibrium. Okay, that's critically damped. Third is heavy damped. Okay, heavy damped. You see the graph? What is heavy damped? It's being compressed from original one. It's being compressed. So this is your x. So this is your x. When you let it go, what happened? Do you come to equilibrium? The spring takes time to come to equilibrium. I don't know how long you're going to take. Very long time to come to equilibrium. So the spring, when compressed, if it's heavily damped, I think after you compress, you go out, you come 2 hours later, maybe after 2 hours later, you can see like it come to slowly come to equilibrium. That's called heavily damped. Okay, light damped, critical damped, heavy damped. Light damped, the one we found every time in your lab, period does not change. Critical damped, never initiate oscillation, straight come to the equilibrium position at the shortest time. Heavy damped, its mission also come to equilibrium, but it take very long time. Any questions from here? Okay, now let me tell you an example, a situation. You tell me, is it light damp, critical damp, or heavy damp? Okay. You know, car suspension system, the absorber, the car, the wheel. The wheel, if you watch the wheel, inside there is a spring, and the spring is together with the damper. You will have a damper at the side. Damper absorbs the energy and stop the tire from oscillating. When the car passes a speed trap, a hump, you go up, the spring will be compressed. When you come out, then the spring going to oscillate. What type of damping must be set in the car? Light damping, critical damping, heavy damping.
Light.
So light damping. So one of you said light damping. The others?
Critical.
Critical.
Unless the spring is designed to be critical.
So you as a passenger, you want to be what damping?
Okay, so passenger critical.
You want to be critical. So the car manufacturer also must damp it in a critical way, right?
Oh, okay.
So the suspension system, the absorber must be critically damped. Okay. If the car is light damped, a big problem, right? After passes the speed trap, I think by the time you reach the house also, you are like oscillating. and down. So it's very bad lah. If it's heavy damp, what happened? If the car is heavy damp, after you pass the speed trap, the spring will be compressed. Then your car at the back, then what happened? I think by the time you reach the house, still the spring will be compressed. It takes time to come down. So not good for heavy damp in the car. The car suspension system, the absorber is critically damped. Okay, another one. Door stopper. The door on the top, when you open the door, you let it go, the door stopper will try to close the door slowly. What type of damping? Inside the door stopper, you have a spring. When you open the door, the spring has been compressed. When you let it go, the spring will expand until you close the door. What type of damping that spring expands?
Heavy.
That's good. Heavy damping. It takes very slow time, more time to reach the close the door. Okay, yeah. So this is 3 type of damping lah. Facts to remember. Any questions about damping? No questions, Okay. So do you want damping? Do you want the oscillation to be damped or don't want to be damped? It depends on the situation, right? Like on the left side, the clocks, like there is a pendulum here. Do you want this oscillation to be damped?
No.
No. So here we don't want damping to happen for clocks. But on the right side, we want the damping to happen. Car suspension system, damping to be happen. The voltmeter and ammeter used in the lab, when the needle goes to one side to give a reading, because inside got one spring tightening it. If it's not damped, the spring inside will start to oscillate. So the needle can vibrate up and down because the spring is compressed and it will be like oscillating. So it need to be damped. Okay. So of course, so conclusion is what? Sometimes we want damping, sometimes we don't want damping. Okay. So this is another important graph you need to plot. Okay. They will give a normal undamped graph. They'll ask you to draw the critical damp one. So critical damp, you remember the red one. I can't remember they asked for the over damp and critical damp. Not even once, I think. Normally they ask for the light damping. So light damping, make sure the period is the same as the undamped one. Okay. Period unchanged. Okay. So you want to do this. You want to do this in the lab, like in the air, it's a light damping, the pendulum. In the thick oil, it experiences heavy damping. In the water, it experiences critical damping. Okay, I think the most difficult one is the critical damping. You need to check what viscosity is required just nice. It stops when it passes the equilibrium without oscillating. So critical damping need technology. Okay. You put too much of density of liquid here in the absorber, it's going to be heavy damped. Too little, it might going to become a light damp. So to be critical damp, they have to check the the viscosity of the liquid used inside the absorber. The car one, I think, is oil. Okay, the car inside the absorber of the car filled with oil. Okay, to damp the oscillation. Okay, so we are towards the end of the topic. So as I said, this is facts. The last part of the topic we're going to do is about resonance. Okay, guys, you learn about resonance already, right? In your Form 4, Form 5, heard of resonance, right? Resonance, good or bad? Or good and bad? Good or bad? Or is good and also bad?
Usually bad.
Usually bad. No good?
Maybe some.
Okay. Anyone can say what is the good of resonance?
You can change channel on your radio.
Very good.
Oh yeah. Oh, okay.
Your telecommunication, your phone. When someone is calling you, you receiving the call. How you receive the call? Because the frequency of your friend's signal and your frequency of your phone frequency, the oscillator frequency is the same. Resonance happen, so you get that signal. So no resonance means no telecommunication. Okay, no resonance means we don't have a very good medical device in your hospital. What is that? The remote sensing, MRI, magnetic resonance imaging, what the full name. MRI stands for what? Magnetic resonance imaging. The R stands for resonance. Okay, so resonance is important for medical field. MRI, no resonance means no MRI. Okay, okay. So anyone, so there are lots of good resonance. What is bad about resonance? Anybody?
When two objects have the same frequency is connected, they will have maximum amplitude.
So why it's bad? Why it could be bad? In which situation resonance could be bad? The damage to the structure, right?
Yes, yes.
If it's rigid. Okay. So let's talk about resonance. What is meant by resonance? So this is the long wording you need to remember. What is resonance? Resonance is a phenomenon. It just happens. It just happens. You don't know why it happens. It just happens. Resonance is a natural phenomenon. The oscillatory system
Sir?
can break the glass, right? The opera singer rise the pitch. If the pitch, if it's quite high, it can break the glass. Okay. So let's use that example here to explain resonance. Okay, resonance is the phenomenon whereby an oscillatory system. Who's the oscillatory system here? The opera singer or the glass?
Glass.
Glass. The oscillatory system, the glass, oscillates at a much greater amplitude. The glass oscillates with a much greater amplitude. This happens when the frequency of the driving force. Who's the driving force here? The opera singer. The frequency of the driving force, the opera singer's pitch, matches the natural frequency of the system, the glass. Resonance happens. Okay. So the oscillatory system is the opera singer. The the oscillatory system is the glass. The driving force is the opera singer. The frequency of the driving force must match with the natural frequency of the glass. Then resonance happens. Okay. So this is happens. This is a phenomenon like it happens. So let's say you want to make heart of your friend. Heart is having a heart. So the heart of your friend to oscillate vigorously. So you create a wave which matches the frequency of the heart frequency oscillation, the natural frequency of the heart. The heart will start to oscillate, but very difficult to do that. The frequency of the heart, I think, is quite high. Cannot match. So this is the idea. Okay, this is the famous setup explains resonance. Okay, the Barton pendulum. The X, we oscillate the X. Okay, we oscillate the X, and E to A will start to oscillate, but the C will oscillate with the greatest amplitude among the A to E. Why C oscillate with the greatest amplitude? Why C oscillate with the greatest amplitude? Because the length is identical. Therefore, what we can conclude? The natural frequency of what same with what? The natural frequency of the C same with the X. So they will oscillate with the maximum oscillation, maximum amplitude. Okay, now tell me, resonance happens in a free oscillation or forced oscillation? Forced oscillation. Okay, remember, resonance always happens for forced oscillation. Nothing to do with free oscillation. Free oscillation, no such thing as resonance. Only forced oscillation causes resonance. Okay, the opera singer break the glass. It's a forced oscillation. The opera singer forced the glass to vibrate more vigorously. Okay. Okay, forced oscillation produces when a body is subjected to an external oscillatory force. The force is called the driving force of the driver. The oscillating body is known as a responder. Okay, so the X is the driver. So opera singer is the driver. The glass is the oscillatory system. It's a forced oscillation. Okay, resonance can happen. Okay, so I go to the last point. The pendulum whose natural frequency is the same as that of a driver will oscillate with the greatest amplitude. This pendulum said to be oscillating in resonance. Okay, resonance. Okay, this is another important graph. One year they asked 3 marks question. Explain the graph. Okay, what is this graph? Amplitude versus frequency. This amplitude of what? Let's say you have an opera singer and glass. This amplitude is amplitude of what? Amplitude of the glass or amplitude of the opera singer? It's actually amplitude of the glass, right? This amplitude of the glass. This frequency of what? Frequency produced by the driver, who's in this case maybe opera singer. So when the frequency of the opera singer raised, what happened? The amplitude, this is amplitude, the amplitude of the glass will rise. The glass start to oscillate more greater amplitude, but the amplitude reach the peak at what frequency? At the natural frequency of the system, at the natural frequency. So when natural frequency, when the opera singer produces a frequency matches the natural frequency system, the amplitude become maximum. Then after that frequency, if the opera singer keep on rising the frequency, what happened? It passes the natural frequency, so the amplitude start to drop. So you need to draw the graph. The graph got 2 types. Light damping. Light damping, the glass, if it's light damping, or spring, if it's light damping, that means the resistance between the atoms is not that strong. So when resonance happens, the amplitude can grow very high. Okay. If the spring at the bottom, we place a big cardboard at the bottom and we start to oscillate it, what happened to the spring? It tend to become heavy damping because big air resistance is going to add, and you put a cardboard at the bottom and you oscillate it together with the cardboard. So the air resistance will be greater. So what happened? We still will get resonance, but the amplitude will be smaller than the light damping. But the peak is achieved at the natural frequency. Okay. But in reality, I tell you, in reality, the peak will move a little to the right, little to the left, sorry, little to the left, like this. This is the most heavy damping one. The heavy damping, the peak will achieve, the natural frequency will get shorter and shorter when get heavy damping. But if you draw exactly the same point, still allowed. Cambridge gives you mark. Okay. To be more accurate, heavy damping, the graph should be a little to the left, to get the peak. Okay. The natural frequency seems affected by the damping, heavy damping. Okay. Okay. So 3 marks question, 1 year they asked, what will happen when the frequency of the driving force is increased continuously? So you have said when the frequency approaches the natural frequency, the amplitude of the oscillatory system increases, 1 mark. When the frequency of the driving force matches the natural frequency, the amplitude become maximum, 1 mark. The frequency more than natural frequency, the amplitude decreases again, another 1 mark. So 3 marks question. Okay. So this is that's all. This is heavy damping, light damping. The graph looks like this. If it's no damping, you have an oscillatory system which has no damping, free oscillation. If resonance happens, how the graph going to look like? No damping. Light damping very high, heavy damping flat, light damping high, no damping. How the graph looks like? It's going to be a asymptote. It's for no damping. And when the resonance happens, the amplitude of the oscillatory system is infinite, theoretically. It means oscillating system, if no damping, resonance happen, you're going to oscillate with the biggest amplitude. I think the system can't sustain, like, going to break. Okay, no damping. Any questions from here? Nice. Okay. So remember this graph, it's very important. Amplitude versus frequency. Okay, so as I said, resonance good or bad? Yeah, there is a danger, there is a uses. The danger is resonance can damage the structure. The most important damage is the bridge, right? The Tacoma bridge. You heard about that? The bridge, this bridge was collapsed due to resonance. What is the driving force in the bridge collapse? The bridge is the driving force of the oscillatory system. The bridge is the oscillatory system.
Yes.
Okay, who's the driving force?
Wind.
Who? The wind. Okay, the wind frequency, it blows such a way that the frequency of the wind matches the natural frequency of the bridge. So the bridge start to oscillate with the maximum amplitude. The structure was damaged. It breaks. Okay, it's bad lah. I can show you one video here. I don't know whether I have that video. Let me check. Hold on. Give me a minute. Desktop documents. Okay, class. Maybe the next class I show you the video. I don't know where I kept it. You can check from the net. Maybe the next class I show you the videos. How the bridge has been collapsed. Okay. So the bridge collapsed, and I think recently, the London Olympic game, which year they built a bridge across the stadium. The people pass by the bridge. It's a newly built bridge. The bridge start to oscillate with the maximum amplitude. The people can't walk. The people move forward, but actually they move sideways. And the Olympic what was organized by England a few years back lah. So what they did, the bridge has been closed for 5 to 6 years, I think. They put some damper, they stabilize it. before it opened to the public again. So it's danger. Resonance sometimes is danger. It's damage the structure. And uses, of course, telecommunication. All musical instrument, the sound produced is actually resonance. Okay, so that's the use of resonance. Okay, so that's all about the topic. So what you learned today? You learn about all facts. The damping, what is meant by damping, 3 types of damping. Then we talk about resonance. What is meant by resonance? Is it good or bad? Then the graph, this graph. Okay, so that's all about this topic. So next class, we'll be discussing the questions. Okay, the past year questions. So go and try to do the past year questions. The questions, the one, this document. Okay, just spend maybe 1 or 2 hours today. Go through these questions. Okay, maybe the first few, you do more, better. So tomorrow we'll be discussing this. Okay, we'll be discussing these questions. Entire SHM. Okay, any questions?
Teacher, the responder, is it the oscillatory system?
Responder is the oscillatory system. Yeah, respond to the driving force. Yeah.
Okay.
Yeah. Responder is the oscillatory system. So yeah. Any other questions? So this SHM topic is a very important topic like gravity. Why? I told you. How many topics are there in A2? You have 16 topics. You will come out 12 structured questions. So maybe three or four topics won't be in your paper. So SHM every year there'll be one. So worth studying SHM. Okay. So give a try these questions. Tomorrow we'll be discussing about this. Any other questions? So no questions, Okay. So I stop here. So I want you to do as homework. Please do the questions here as homework. Look at the question. The answers at the back, but don't view the answers first. You do your questions, check the answer, then we can speed up the process of discussion. Okay, we just can go the one you got problem. Okay. Any questions? So no questions. We stop here today. See you tomorrow. Okay, bye.